Hello, everyone. This is Professor Jeff Wilkerson at Luther College with an introduction to exercise 28, I believe it is. Yeah, exercise 28, the absolute magnitude of a quasar from astronomers as observers and experimenters, published by Kendall Hunt. In this exercise, so this is a great exercise to look at an active galaxy. You're going to look at active galaxy 3C273 and try to understand a few things about this galaxy, this active galaxy, this quasar. And so one of the things that you'll do is to start with trying to find an apparent magnitude of the object. And to find the apparent magnitude of the object, there's your object right there. I think what you want to do is you want to use your digital calipers and measure the diameter of the object on there. And as you measure the diameter of the object, measure the diameters of these other objects of known apparent magnitude and compare that diameter to the diameters of these other objects to try to get an estimation of an estimate of the apparent magnitude. So what of 3C273. So probably a good way to do that is to get a magnitude as a function of diameter on the image. And probably the scale is, even if the scale weren't linear, okay? You can imagine having magnitude versus diameter look something like that, and that's okay. You can fit a curve to it, what we would call an empirical curve that doesn't really have any absolute meaning, but then you would find your diameter of 3C273 and read it across right there and get the magnitude. Or you better yet, you just use the functional fit. You just, whatever your computer tells you is the form of that fit. Use that equation to determine the magnitude given the diameter of 3C273. Probably that's not the case. You probably don't have to deal with that it's more or less linear, that there's a linear relationship between size and magnitude, diameter and magnitude, say in millimeters, and magnitude up here. And probably you can get away with fitting a line. And then you can use the fit of that line, the slope of that line, and the intercept of that line. Use the equation of the best fit line. I'd use a computer to do it if you have it, but you can use graph paper otherwise, and do it by hand to get the slope to tell you what the relationship is between magnitude and diameter. It's probably worth taking a moment here to pause to say, why does diameter of this image depend on the magnitude depend on the, why are bigger objects, why do brighter objects look bigger? Because remember, these are objects we're not resolving. We're not seeing the surface of them. They're not necessarily actually bigger. They might be, they might not be, we don't know. So we're seeing the light that's blurred out by the atmosphere, and we're seeing the image of that light spread out. We're not actually looking at the surface of that star. It's not resolved, okay? So those stars get their light blurred by turbulence in the atmosphere. And if you made a graph of the intensity of light as a function of position on your film or on your CCD chip, it would look something like this, a sort of Gaussian shape. But it turns out that the sky background, let's just go ahead and have it normalized to 0 where we would expect it to be. But the sky's not uniformly dark. You have a sky brightness background that could just be noise in your CCD chip, but more likely is background scattered light in the sky. And so you have a limiting magnitude. You'll talk about the limiting magnitude, the faintest object that you could see before it disappears before the background. And if that is here, you're going to see the object have a width that looks something like that, because that's where it gets above the sky background. If you have a brighter object, it's going to look wider to you because it's more of its light. It's further out on the tails of the light distribution before it fades into the background, the sky background. And so you're going to see a brighter star look bigger, and thus you get this kind of relationship. So that's one of the things you do in here. I would probably do that first. I think the lab's written for you to do this second step, but go find the apparent magnitude of your quasar 3C273 and see what its apparent magnitude is by comparing it to the magnitudes of stars that you see there on that finder plate by measuring their diameters. And then you need to figure out what its redshift is and to say, okay, if this redshift, if this is part of the Hubble flow, if this is part of the expansion, the redshift is due to the expansion of the universe, we know the Hubble Lemaitre law tells us that the velocity of recession is equal to h naught d, and we can calculate distance by velocity over h naught, and we can get velocity as we've done many times in this text throughout the exercises. Go back and look at all of them. We can get velocity as v over c is equal to delta lambda over lambda. So you can use figure 1728.1, excuse me, here's figure 28.1 to measure that shift. So you see the positions in the spectrum of the h beta line, for example, right there, and that's where the h beta line would be at rest. And so you can figure out how far it got shifted this direction. So you go in and measure it with your calipers. That's a big enough shift. You can probably just measure it with a ruler across there and get a reasonable get a reasonable measurement of it. I'd probably go ahead and measure it with my calipers just because it's going to be a little bit more precise. So I would measure it with my calipers across there. And that tells me how far it's shifted on this picture. As we said many times before, in other videos, maybe you're just watching this for the first time, you can go find this. When we're dealing with the spectrum, we could have printed this picture any size we want to. And so we could have made this a huge picture, a tiny picture. So we don't know what that shift in millimeters across this picture exactly means until we convert it to wavelength space. To get this delta lambda out of there, we need to get the scale of this plate. We need to get this, figure out how many millimeters across here is equivalent to how many angstroms shift. And to do that, you can look at a couple of known lines, for example, out there. You got a 60-30 angstrom line and a 38-89 angstrom line, and you can measure their separations on the plate. So go ahead and measure right there on the plate the spacing between those two lines, and then calculate the wavelength difference, 60-30 minus 38-89, and calculate a sort of dispersion, a plate scale in this case, for this to say delta lambda, to say that the change in angstroms, the 60-30 minus the 38-89, divided by the shift in millimeters is going to give you angstroms per millimeter on this picture. And so if you multiply, that's a conversion factor. You multiply each of your wavelength shift measurements by this angstroms per millimeter, it's going to give you a conversion of shift in physical space on this picture. So many millimeters on this picture times your conversion factor is going to give you delta lambda in angstroms. So delta lambda is equal to the shift in millimeters times that conversion, your plate scale, angstroms per millimeter. And so then you go and you calculate the distance. You calculate the recession velocity, you seek the recession velocity in here, you use the Hubble constant and the Hubble Lemaitre law, and you calculate the distance. And then you can say, distance is equal to 10 to the m minus m plus 5 over 5, or the log version of that that's given to you in the lab. I think it's given to you in the activity right here. You have the absolute magnitude is equal to m plus 5 minus 5 log times the distance right there. And you can go and use this and you calculate the absolute magnitude, and you can compare that absolute magnitude to absolute magnitudes of other objects and get a sense of how stunningly luminous this object is. Then there's a piece to go on to talk about the variability of the object. The whole idea there is that information can't travel faster than the speed of light. So the left edge of an object can't know what the right edge of an object is doing any sooner. So if the right edge of an object starts to do something, the left edge doesn't learn about it any faster than the time it takes light to travel across that object. So variability, if you get an object that's varying hugely up and down, it helps you put rough limits on the size of the object to say if it's changing luminosity a lot, then there must be something going on with the whole object. And so the whole object must be doing something coherently, and it tells us that the size of we could estimate what the largest size of the object that could be doing that. For example, you could imagine a flare on the sun causing the sun to get brighter. But a flare on the sun is not going to cause the sun to get 2 times brighter or 3 times brighter unless it's a very odd type of event. If you looked at the sun and the sun got 2 times brighter, probably had to be something that went on the entire sun or most of the sun. It's not something that just happened in a localized event to make a change in brightness and luminosity of an object that's comparable to the entire luminosity of the object. So we walk you through that, and you have a chance to think about that a little bit. So again, as we've seen in many other activities, one of the learning goals you might have here would be just to better understand the use of spectra and use the Doppler shift. We've used the Doppler shift, use spectra to get speeds to make physical models of systems. It is such a common activity in astronomy. It has been a common activity in astronomy for a long time now, that this is really valuable practice for us, and we practice it again and again and again. And you see that here. Understanding the quasar, to see the path that we got to. So this was really hard for astronomers, really hard for astronomers to come to terms with the idea that a quasar might be so luminous, that it might be emitting so much energy, because then you have to come up with a model for where the heck is that energy coming from. And that's a challenging thing, is to say, especially in something so small. And so we end up in the supermassive black hole realm, and to say, but it's hard to get there. It's really hard to envision something that luminous, emitting that much energy per time in the universe. And so this is a way to walk you to the path to see all of the pieces of information that led to astronomers making that model. So it helps us understand, sure, the absolute magnitude of the quasar, but maybe more importantly, helps us understand the process that it took for us to get there, and to see what we had to do to become sort of comfortable with the idea that quasars could be very distant and very luminous like this. And then another piece of this, if you wanted to think about another outcome you might be seeking in an activity such as this one, it's this idea of converting image size on a plate to magnitude. This is something we don't do as much anymore, because with the computer software, with digital cameras that we have around right now, so you get a pretty quick conversion to magnitude from the number of electrons that were liberated in the CCD chip and the CCD pixels for your object. And so you don't always go through this step anymore, except much of the work that gets done, you're often comparing an object. If I'm looking at the star that I'm seeing and I get access to data from 1950, I might have a picture of my field that somebody took in 1950, and I want to convert that to magnitude system. I want to convert all the stars in there, because I'm studying that field now, and I want to know what's changed. Which of my stars are brighter? Which of my stars are dimmer? And so that's very important data. I have to go back and do it this way. I have to go back and measure the diameters of the objects and do those conversions, just like you're doing in this activity. So people do still do this. It is still an activity that is undertaken. It's just not as common as it used to be. It used to be the only way to go about doing this. So anyway, dive in. Enjoy this activity. Think about the vast distance, the vast luminosity of 3C273 and the other quasars and the other active galaxies that are out there. Good luck with it. As always, let me know if you have any questions.